Hello, everybody. Welcome to our webinar for today. And today, joining me is Edouard. So Edouard Leonard is our senior wind engineer. So thank you for being here today, Edouard. And so he's the expert that knows the software in and out, even more than myself. And so you have a chance to ask him today some questions. So just if you have any questions, just let us just type them in. And in my case, maybe some guys know me. My name is Juan Camilo Daza, so I'm the business development engineer for Meteodyn. And so yeah, so let's get on with it. So this webinar is about the 1.9 version, which has just been released, and you guys will get it very soon if you don't have it. And we'll make a few summary as well concerning some important advices that we have for you guys today. Okay, so Edouard, go ahead.
Yeah, hello, welcome to all of you to this webinar. For those who are not familiar with the software, I propose a short presentation of Meteodyn WT. Okay, this is a good opportunity to discuss also about the best practices related to the mapping. So this is a key element to understand how to control on the mesh accuracy. And then, of course, we will present the new features of the 1.9 version. So here you have the wind resource assessment methodology. Okay, so we start with the pre-processing. We provide different modules, okay, in order to import different maps, so orography maps and roughness maps, create the wind turbine type, import meteorological data, okay. Then we can go to the next step. So the first step is the site creation. So we have a circle area where we can, of course, define the wind farm. So this is where we can place the turbines, met mast, the mapping, and other elements. Then we go to the second step, okay, based on CFD computation. The idea now is to compute, to solve Navier-Stokes equations, okay, to determine the wind flow in the site. And then we can use the wind rows, okay, and the CFD results to do what we call the synthesis computation. So this is what we need to get the wind resource assessment results. So wake effects, winds, AP, AP, IC, and so on. Well, just to start with the step one, so this is the site creation. You see here that you can have, so this inner circle is the site. So we can define mappings. You can see here mast and wind turbines. And of course, this circle is defined by the center, latitude, longitude, or X and Y, and radius. Okay. Then we go to the second step. Okay, so this is the CFD computation. So what we do, we're using different synoptic sectors, and for each sector, so we generally recommend a 20-degree sector step, maybe more with more accuracy in the prevailing sector. Okay, for each sector, we will compute the Navier-Stokes equations to see how the wind flow evolves in the site. Okay, so just to describe our tool, so this is we're providing very simple CFD configuration. Okay, so just in a few clicks you can launch one computation. We have an automatic mesh refinement around points. So this is, I will explain this point in the next slide. So this is a very good compromise between precision and computation time. Okay, we have a homemade medial solver. Okay, so of course this enables us to conduct research to improve continuously the performance and the convergence of the line WT. The fast, so the CFD computation is very fast. So just one example here to show you the strengths and the performance of the CFD tool. So with the radius about 12 kilometers, so this is standard site, okay, we need 10 million cells, okay, in the mesh, and this is in terms of RAM, we need 11 gigabytes. Okay, so with one core, for example, you need 1 hour and 20 minutes to launch one sector. If you want to do the multiple core computations with 4 cores, you need just 25 minutes, okay, to launch one sector. So it's very fast. So one strength of this software is also to consider the thermal stability conditions. Okay, so this is a hot topic in the wind resource assessment field. So I will explain this, and we were providing here a new method to determine the conditions. Okay, and we provide many tools to analyze and improve the convergence. Okay, so you have an automatic conversions tool. You can estimate memory and so on. Many tools. And in the advanced options here, you have what is the post-CFD computation. So this is a very interesting tool that enables you to compute, to get results after the CFD computation using an interpolation process. And you will see with this version, the performance has been improved. Okay, so let's have a focus on the mapping and the surface mesh. Okay. So what I previously said that we were using a structured and oriented mesh. So it means that we have small rectangles to describe the mesh. And you see here the mesh is moving according to the prevailing sector. So what is very interesting in this tool is that we are using automatic refinement at the result points. Okay, so it means that close to the interest points, the mesh has a minimum horizontal resolution, and this is what we get, what we can define as a input parameters. Okay, and then we're using a horizontal expansion coefficient. Okay, to increase little by little the size of the cells. So this is what I want to highlight here. You see one example with mapping. So it's a 2 kilometers by 2 kilometers mapping. You see here, if you are using a step of 1 kilometer, okay, here, you see we have 9 points, okay, with small cells around these points. And inside of the square, we see very big cells, okay. And if we're using a more appropriate step of 50 meters, okay, we see that, of course, all the mesh inside of the mapping is very precise. So that's why I recommend to, of course, use mapping on all projects with a suitable precision. So 50 meters is generally recommended. Just to finish on this mesh generation, what about vertical mesh? So we have a very similar process, but we're using an automatic refinement at the ground. Okay, so you see here, by default, the first 10 cells close to the ground have the minimum cell size. Okay, so 4 meters by default. And then we are using the same process, so we have a vertical expansion coefficient, of course, to increase little by little the size of the cells. Okay, and then we go to the last step, so what we call the synthesis. So this is the main process of the synthesis is the meteorological data transfer. So the idea is to transfer the frequency table from the meteorological mast to all points of the site, and of course, wind turbines and the different points of the mapping. And of course, we're using the CFD results to do this transfer. Okay, so just to show you briefly the software. So this is the 1.9 version. You see here we have a list of different sites. So the software is not based. You see all the projects here with some description. Okay, if you want to open one site, you can go here. You have this page, okay, related to the simulation. You can define the location here, different maps. Of course, we provide databases and maps to launch the computation. Then we go on the elements here. So you can define with the ranks different mappings. So mapping is the grid of points. Okay. Then we can go on the CFD panel. So here you see that each tile corresponds to one CFD computation. Okay. With here, for example, 20 corresponds to sector 20, and the 0 to the stability 0. Okay, we can check the convergence, see the results, and so on. And then we go to the last step. So this is the synthesis. Okay, and you see here some results. Okay, you have here, for example, the prediction. Okay, you see the prediction of this project. Okay, so of course. At the end of the synthesis, you can get the standard results. Okay, so wind farm parameters, AEP, time series results, And you can also have access to the advanced wind resource assessment results. So typical options and modules are here. So you have the curtailment, multi-mast computation, multi-stability computation, access to the IC components, results, cross-validation, and the mesoscale microscale coupling. I let Juan continue with the new features of the version.
Thank you, Edouard. So we have a couple of new features. So the software's been improved in general. The overall performance has been improved on the software. So you might see little changes on the interface. So this is just to make your life easier, but also so that the software is much more fluid and you can work faster. So for example, in the synthesis creation, we improve the performance here. Imagine you were to have a wind farm of 200 wind farms. This is now much better organized, and the software is going to take care of it much more quicker as opposed to previous versions. So yeah, so in the case you have a lot of data, you'll see these improvements. In the case that there's not a lot of data, it's going to be just as fluid as it was. We have also optimized some processes behind which you never see, but they might make the software run a little slower. So we've optimized this, and now we can get rid of all these orphan files, which are not really useful files. So sometimes they duplicate, etc., for imports and stuff. So as well, there is also an administrative tool. You cannot run it at the same time as the software. This is why I'm not going to show it, but it is there, so you can clean these orphan files, etc. Okay, so let's move on to the next slide. So talking more about how the performance has been improved. So now we can treat geographical data faster, especially for big roughness files in shape format. And also there's a faster treatment vector files or shape and map files for both roughness and orography. So now you can click on the button that you see here on the right top side, and it's only to be used for big files. Don't use it for small files, because when it's a small file, it's gonna cut the process. So only do it for big sites. And also the export citing process has been improved. So in some cases, the processing time has been reduced by a factor of 10. So I guess you guys be happy to be exporting your projects much quicker. If you're running post CFD computations, only do this, by the way, if you created a mapping for the whole site. If not, don't do it, please. If you're running post CFD computations now, they're going to be faster, and they're going to contemplate multi-core computation, which they didn't previously. So this is also going to save some time. Okay, so moving on to the next slide. Again, some things, functionalities to make things just easier for you guys. So now you can export the log files directly from the software before you have to go into a specific folder. Now you can do it from the software. Now you can look for elements, and there's a search box added to the element panel. So in case you have many elements, you can look for one. Before, like I said, if you had 200, 300 wind turbines, it's going to be hard to find. You can also organize the layouts for the synthesis computation. This is also has been made much easier for large layers. The maps, we have included additional maps. So there's, as you know, there's a maps behind the software sound. So now there's more maps that are available behind the software. So there's a satellite map, contour lines, hill shading, etc. And this map service is independent, so it runs from OpenStreetMap. And you can, of course, change the order of the topographical elements for the overlapping process. Edouard, can we look at the maps here just for a second? I just want to show this part. So when you're in the main part of the software, here you can click on the visualization, and then you can see that we have different maps. So if you click on the line coming down, you can see that we have different maps. So Here you can see all of them. It was changing one or the other, but I know you guys can play around and you'll see a lot of different maps. Thank you, Edouard. Okay, moving on to the next slide. So for the CFD computation, so you can define job priorities for each computation. So before it was just kind of first come, first served. Now, if you know that you have some projects that are much more urgent than others, you can prioritize this task. Also, if the convergence happens to be lower than 90%, there will be a little warning sign to tell you that you might consider relaunching the CFD computation. So you can do this. But this didn't happen before, so keep this in mind that this is just gonna help you visualize problems if you have any. And of course, you now can launch a competition again, whether it has failed or whether it has succeeded. Before you need to delete it, now you can just relaunch. So this is gonna help you out, guys, quite a bit. So moving on to the next slide, I'll let you take this one, Adar.
Yeah, so thanks, Juan. Let's now talk about scientific features. Okay, so the Catalan module is available in the software since now the 1.7 version. Okay, but we improved this module, providing more flexibility in the Catalan process. Okay, so one example is the hysteresis conditions. Okay, so you see here one example without hysteresis and with hysteresis. For example, in yellow here we have the operating mode, and in blue we have shutdown mode, for example. Okay, but we have these small fluctuations. Of course, we want to avoid on-off effects in this curtailment process. So using some hysteresis entering and leaving conditions, okay, for example, 1 meter per second and 2 meter per second, we can avoid this on-off effect to have more precise and advanced control of the curtailment. Let's now talk about the thermal stability determination methods. So in previous work, we showed that, of course, the thermal stability has a strong influence on the wind speed and the DEP. Okay, so this is also a hot topic each year in all congresses. But the main question is how to determine the stability conditions on one meteorological mast and more generally speaking on one wind farm. Okay, so in previous versions, we were recommending and providing two different tools and approaches. Okay, so the first one was the method based on temperatures. Okay, so it was based on two temperature sources and one speed source. And the idea is to calculate the median Bukov length for each time step and deduce the Meteodyn thermal stability class. Okay, but of course, it requires two temperature sources and high measurement accuracy. And of course, this is not frequently observed in measurements. Then we have the shear calibration approach. Okay, so this is based on the wind shear calibration. On one hand, you need to launch CFD computations for different stability categories. Let's say unstable, neutral, slightly stable, and very stable. And on the other hand, we need to analyze the shear measurements. Okay, so you can analyze per hour of the day, per month, and per sector, for example. And then we compare the measured shears and the simulated shear values. Okay, and we deduce which stability class enables the best fit. Okay, so you see, this is maybe the more robust method, but it requires a long time to analyze the wind shear, launch the computations, and then transform all this in new time series, okay, into meteorological data. So in this new version, we are providing two different approaches. So the first one is based just on the wind shear, so dedicated to offshore or very flat terrain. Okay, so the idea is just to define some thresholds of neutral winds and then deduce stable and unstable winds. Okay, so I'm not focusing on this one because it's just on offshore side. But the last one is very interesting because it's based on shear and TI. Okay, so you just need to have the wind shear and turbulence intensity information at one mass location to use this approach. So you see, of course, very interesting because we can use it in maybe all projects. Okay, so you still have the same computation box to launch this approach. Okay, so you have just to select the shear plus TI approach here. What about the theory? So this approach is based on the work of Lasse Svenningsen, okay, who developed this approach some years ago. You can see more information here. So first of all, we estimate the neutral levels, okay, of the shear and the TI. So for example, you take the windrows, you divide it into several sectors, 20-degree sectors, steps, for example. You consider the high winds, okay, so 3% of the speed, so the highest wind speeds, and you compute the shear and the TI of these high wind speeds. So we understand here that we need a large time series, of course, to get a representative values, okay, because we need to consider this 3% of very strong winds. And then we estimate the normalized deviations of the shear and the TI using these different formulas. Okay. And then using these deviations, we can use these conditions to deduce the neutral, stable, and unstable conditions. Okay. So for example, the stable correspond to a small deviation of the TI and a large deviation of the shear. And finally, we can estimate the Molin-Obkoff lengths, okay, using these different formulas. And of course, you can find more information in the paper. So we validated this approach on many sites. So here you will find one focus on some sites. So we published some papers and posters on this validation. So you have one flat terrain, so this is a Cabao public site containing a lot of data, okay, so temperatures and a lot of sources. So it's, okay, you can see here, very flat terrain. And we're also using a complex, very complex terrain. So you see here the altitude evolution, okay, in that site. So very interesting site because we have at least 1 year here, temperature, wind speed, and standard deviation data. Okay, so you can find here the comparison between the three methods. Method based on temperatures here, method based on shear calibration here, and the last one, so the Svenningsen, also called shear and here called TI. On the simple side and complex side here. So in white, you can see the very unstable classes, and in green, dark green, you see very stable. Okay, so what we observe on these different tables is that for the simple side, we have very similar behavior, okay, for the three methods. We see this I shape, okay. So of course we see that we can deduce with the three methods the day and night transition, okay, with unstable cases during the day and stable during the night. But we can also determine the seasonal variations, okay, of course, with this I shape, which is also, of course, common in the stability analysis. Okay. And then if we have a look on the complex side, so it's also very interesting because we see that we have something very similar. We can catch the day and night variations, okay, from unstable to stable. If we have a look on this very complex side, we see that we are probably slightly underestimating the very stable cases, okay, but it's not a big deal. We are just observing here, for example, the class 4 instead of class 5. Okay. So you can find more information here on these different papers. Just to show you how to use it in the software. So it's the same idea. It is available in the meteorological data module here. Okay, so we can open one meteorological mast. Okay, so for those who are not familiar with the software, we have here general information. Okay, we have the location, ground elevation. We have the measurement period here. So you see we have, in that case, 1 year, around 1 year. Okay, so then we can just select the reference height. Okay, we can use this computation tool. Okay, and we can compute the frequency table and the stability class. Okay, so when we open this module, you see you can select the temperature or other methods. And here you can now select the shear plus TI corresponding to the Sphenixian approach. You have here superior height to compute the shear, inferior height 60 meters. The height for the direction, recommend to use the highest height, and the height for the standard deviation, the same. Just click OK. So yes. And you'll see in a few seconds we can launch the tool to get now a new time series of stability. Okay, so you see now in this time series, you see a new column called stability, of course, corresponding to the stability information for each time step. Okay, so just to have a focus here on the comparison between different methods. Okay, so the method based on temperatures is probably the most accurate method. Okay, but we need, of course, precise temperature measurements, and this is, of course, something not always available. We have the shear calibration approach, so very interesting and maybe the most robust, but it requires multiple computations for calibration, and of course, long analysis time. Okay, and this Sphenixian approach or TI method, so it has been validated on simple and complex terrain. Okay, but we need at least 1 year data, okay, to get a representative um, values of the shear and the high wind speeds. Okay, I recommend you to use different approach. Okay, of course to compare the stability information, and of course you can check the daily evolution. So this is a good way, okay, from unstable to stable, to check day and night variation to see if the measurements were accurate enough to determine the stability. Fun. Let's speak about very interesting case.
Thank you very much, Edouard. So yes, very important that now you guys have additional methods to calculate the stability, and this is going to save a lot of time, for sure. So there was a case study, very recent case study done in a wind farm in Ecuador. It's called Villunaco Wind Farm. So this farm has been modeled in WT by a client of ours. It's just a few details on the wind farm, 16.5 megawatts, and they have compared the AEP estimation with actual SCADA data, production data, and what was found was that the difference was only around 2%. So we're very proud of this project, and thank you very much to the Universidad Nacional de Loja in Ecuador and to the Centro de Investigaciones Tecnológicas y Energéticas in Brazil, CP. So yeah, this paper has been published. If you guys want to look at it, here we have the details. If not, any questions that you have for the webinar or anything else, of course, you can contact me or your business development engineer for your son. Okay, so let's look at the next slide, Edouard. So to conclude on this version, basically the performance has been improved. A lot of stuff behind that you guys won't notice, but you'll notice the software is much more fluid. Some things have been made simpler just to help you organize stuff, and so it's more friendly. We have the biggest thing is the new way to determine the stability conditions. This is a huge method, and of course everything we do is, of course, to improve accuracy, improve software performance. And so, as we saw from the recent study performed, we're very happy with the results. So, guys, if you have any questions, now's the time to type them in. I'm gonna read them out, and we'll see what comes out of it. So, let's see if we have some questions. So let me look here. So we have a question. So what is the difference between the shear calibration method and the shear for offshore method when calculating the stability?
So the shear calibration, so you need to launch what we do. We're comparing the shear values, okay? So it's comparison between data and simulation. So this is why I'm saying it's very robust, because for each time step, okay, you are comparing the shear. Okay, so if you want to use the offshore shear approach, it's automatic method. So we are just defining the neutral levels using the same approach as the same paper. Okay, but because we don't have now the TI the on the site, and because of the complexity of the site, so it's very simple. Okay, just to deduce the information from the shear. So it's automatic method, while the other approach is based on shear comparison.
Thank you, Edouard. Okay, so this is another next question. So relating to the wind study that we just mentioned, uh, did we get the wind data from the SCADA for this case study? We didn't get the data because this study was done by not by us. It was done by the two institutions, are not us, but they did compare the actual production SCADA data with estimated AP calculations done in Meteodyn WT. Of course, they did this when you estimated, you do it as if you only had mass data. Okay, so let's look at other questions that are coming in. Okay, so there's another question here. Which version would you recommend for complex terrain? I'm guessing they're talking here about stability calibration. So Edouard, I'll let you take this one.
Yeah. So theoretically, the best approach, is based on temperatures. So that's why we developed this approach some years ago, and now we have a good feedback on this approach. But we know that, of course, it is not temperature sources are not always available. So, of course, if you want to create a new wind farm and you need to implement a wind mast, it's of course very interesting and precious to get two temperature sources. But of course, we need a good accuracy also for this. So it's a lot of limitations.
Thank you, Edouard. Okay, so next questions from one of our new clients. So, is the update to the 1.9 version automatic for anybody who owns a Meteodyn license? So, I'm gonna send everybody an email, everybody of my clients and my colleagues who are the different business engineers for their zones. We're gonna send an email to deliver you guys the 1.9 version. Some of you guys may already have it if you're in recent contact with the support. So don't worry about that. You'll receive an email, and of course, if you haven't, you can always shoot us an email, and we'll let you know what's going on. Okay, so moving on. So next question: could it be wiser to calibrate wind shear for day and for night times rather than using average wind shear? And is this something you have tried to do, and did it show any added value? Edouard, I'll let you take this one.
So yeah, the day and night approach is, let's say, the basic approach, but of course it's also interesting to consider in the first step. So just considering unstable behavior during the day and stable during the night. Okay, but of course here the interest is to, so it depends on, of course, on which method you consider. But if you are using the new method, so this is an automatic approach, you are doing it time step by time step. Okay, so we're using the neutral levels, okay, to get some thresholds. But then, of course, you are computing the small deviations, small fluctuations of the shear and the TI for each time step. So you can deduce the hourly evolution of the stability. So of course, this is very accurate.
Thank you, Noah. So we have another question. Do we need local measurements for the calculation of stability? So
So this is a very good question. You probably know that using the mesoscale approach, you can have access to this stability information through the Monin-Hobgoff length. So using WRF computation. So this is also of course, it's also very interesting to compare the mesoscale results with the local measurements. But of course, using precise measurements on your site is the best way. But if you have access to mesoscale data on one site, it's the best way would be to compare all different approaches.
okay, next question. So how to add stability to the measurement time series for the comparison?
Yeah, so this is also this is maybe the main reason why this method is robust and interesting, but difficult to apply on one project. So the idea is to get some this kind of tables. Maybe I can show you here more clear. So when we have these different tables, okay, um, so you see you can do one shear analysis with the hour of the day, okay, here, and the seasonal variations. So we're providing one tool called WDA to get this shear analysis depending on the hour of the day, the months, and the sector. We can do it with window grapher or other software, of course. So you can deduce these tables of stability, and then the work is to transform this table into time series. Okay, so you need some manual coding to transform this kind of tables in time series, and of course, requires some process in your to get these tables.
Thank you, Noah. So talking about the paper we just discussed, are the results based on wind farm level or a turbine level?
Sorry, I didn't get the
Sorry,
question.
so talking about the Yonako wind farm that we just
Ah,
talked about, are the results based on the wind farm whole level or on each wind turbine individually?
Yeah, so in the paper, so of course, would be interesting to discuss with our clients at the University of Loja. Um, but in the paper, you see the evolution on different wind turbines. Okay, so I don't know if they're planning to present these results in maybe the next Wind Europe. I don't know, but of course, it's a very interesting study. Yeah.
Okay, we have a few questions coming in, but we're gonna take them. We're gonna take them. It's a client of ours. So, what is the best way to calculate the stability correctly if a mast were to be on the top of a hill and the shear is affected by orography, and they do not have temperature measurements?
Yeah, so you know the idea of the shear calibration. This is why I'm saying that it's very robust, because of course we're using the software to deduce the shear, okay, of the real site compared to the shear of the automatic method. But actually, it gives very good results, okay, because you are analyzing the shear at 80 meters, okay. So for a small range, of course, um, the considering this shear, sorry, evolution in this range is suitable, and of course gives good results.
Thank you, Edouard. Next question, also about stability. So, in complex terrain, do you expect stability patterns to change from one location to another? Or does the calibration at one location guarantee the stability will be calibrated for other locations?
Yeah, so this is also a good question. We assume, and this is one assumption on Meteodyn WT, that the stability is homogeneous on the site. And of course, this is not true if you are working on very large sites. Okay. So yeah, definitely this is one strong assumption. Maybe in the future, because of course the size of the wind farm are growing faster and faster, it would be interesting to have the possibility to define different areas with different stability. But in most cases today, okay, we see that of course the stability is something homogeneous on one side.
Okay, we have another question related to the same subject. So, if you have both temperature data and shear and TI data, would you trust the results of the temperature method more or not?
Yeah, definitely. So you see that in the temperature approach, you are measuring the heat flux. So you are directly determining the Monin-Obukhov length. Okay, and of course the Svenningsen approach is let's say indirect method to determine the, the stability class. Okay, so if these results are reliable and you see the day and night evolution, even seasonal, you see this I shape, of course, the temperature is maybe the reference approach.
Okay, we have a last question. So, it's a bit long. So, after calculating the time series of thermal stabilities with the new method, how can we use them in directional computations? Uh, so, in this case, we calculate this for each time step. So, of course, the time step in question will consider the stability class that corresponds this, and in the synthesis, of course, we're going to take care of this. So, moving on with the questions because there's two parts of it. So, I've always used the method WSH, and in this method, you're selecting manually the stability for the sectors you're interested in. And I wonder how to use this calculated time series of stabilities in calculations.
Yeah, so maybe this point was not clear. Actually, so this is the simple way. When you are using time series, everything is automatic. So when you are selecting configuring a new synthesis, okay, you see here. Um, so let's try. Okay, here. If you select the metallurgical mass, okay, so let's try with this one. Okay, you should see here the stability information 0, 1, 2, 3, 5, 6. So it means that the automatic tool determines these different stability classes. Okay, and that's all. Then you just need to select the different stability classes you want to use. Okay, and everything is done automatically. So it means that you will apply the methodological data transfer for each stability class. Okay, so we consider one frequency table for each class, and then we are using weighted average process at the end to get the average, weighted average, mean speed, weighted average AEP, and so on. Okay. So of course, this is why we attach high importance to work on automatic methods because everything is easy to configure and to launch. Okay.
Thank you, Edouard. So there's some more questions, but they're not really related to the webinar. So anyway, we're gonna answer all the questions. Sorry, maybe there's one last question still. Hang on. Have you studied the difference in performance between using the main stability per sector instead of the time varying stability? Not sure I understand the question.
Yeah. So you know the stability information is I totally agree. Well, it mainly depends on the hour of the day, okay, the months, and the sector. So these are the three main parameters that can influence the stability. And of course, if you have one site very close to the sea in a very specific area, the sector will have a strong influence, probably using a stable behavior coming from the sea. Okay. So of course, it depends on each site, and you can let's say the main approach is using hours a day, months, and sector, but you can adapt this approach if you see that you have a strong influence of the sector.
Thank you, Edouard. So one last question. If you're using statistical data rather than time series data, would you recommend using the average stability?
So you know, for the synthesis, so the main computation is based on statistical data. So even though you are using statistical templates or statistical, the approach is similar.
Thank you, Edouard. So anyway, guys, as I said, all the questions will be answered through email because there's a lot of them. But I think we got most of it. So thank you, everybody, for being here with us today. Thank you for listening. You will also have access to the complete webinar in case you were a little bit late. So you'll get those in an email following you. Any questions you have after that, of course, you can always ask me or your business development for your zone or the info email if you forgot us. Anyway, thank you very much, everybody. Have a
Thanks.
good day, good week. Bye bye.
Have a nice day. Bye.